talk about submodular maximization with the Knapsack constraint.
Thank you very much, Steffi, and thank you for inviting me. So this is based on joint work with Hui Nguyen, who is at Northeastern University, and he's also visiting for the entire semester here at Simons. As the title suggests, we're interested in the submodular maximization problem with a knapsack constraint. So we have n items. Each of them has a cost. And we have a function f on these items, which we assume throughout the talk to be submodular and monotone and also non-negative. And our goal is to select a subset of these items that have costs, let's say, no more than 1. And subject to this, we want to maximize the value of the function. So this is probably many of you have seen this problem before. You'll immediately recognize that it's NP-hard, even for a linear objective. And you might also know that we can get a 1 minus 1 over e approximation in polynomial time for this problem. And this is tight in the value oracle model, which is what we assume here, even if we have a cardinality constraint. So all of the costs are the same. So what we'll be interested in doing today is understanding how can we achieve an approximation guarantee that is very close to 1 minus 1 over e as fast as we possibly can. So the focus will be on running time. But before we get there, let's think a little bit about how do we achieve such an approximation guarantee. And here, we can take inspiration from the classical knapsack problem, where we have a linear objective. And one of the strategies that we can use there to get good algorithms is to guess some of the more valuable items of the optimal solution. And after that, simply pack items using a density greedy. So we sort the items according to their density. So density means the ratio between the marginal gain or marginal value and the cost. And we greedily pack items according to density. So this makes a lot of sense in the linear case. But what do we mean by guessing the most valuable items in the submodular setting? Okay. So what I mean is the following. So let's consider the optimal solution. And let's think about ordering the items in the optimal solution in the following way. So first, the first item in this order will be the items that has the largest marginal gain on top of the empty solution. So we take that item. It has the largest singleton value, so we set it aside. And then after that, the next item that we put in the ordering is the one that has the largest marginal gain on top of O1, this first element we selected. So we can greedily order the optimal solution in this way, in such a way that at every point, the item that we're going to introduce next has the largest marginal gain on top of the items in opt that came before it. Okay, so this is what we call the greedy ordering of opt. And this allows us to talk meaningfully about valuable items. So what are the valuable items? So you can think of it as the first few items are the most valuable. So as we go further along in this ordering, the marginal gain of each of these items starts to decrease more and more. So what we can show is that it suffices to guess the first 3 items in this ordering. So this will be the most valuable items that we really want to make sure we have. And after that, we can actually simply use density greedy. And this suffices to give us a 1 minus 1 over e approximation. Okay? But what is the running time? So the running time is n to the 5th, right? So we're guessing 3 items. So there are n cubed triples to consider. And for each of those, we're using density greedy, which runs in quadratic time. Right, and just to be clear, throughout the talk, I'm going to abuse the term time a little bit. So what I mean by time is actually the number of times we evaluate our function. So for the algorithms that we're going to consider, that dominates the running time, and I'm going to simply assume that evaluations are constant time. So we can use an n to the 5th time. If we're happy with losing a little bit in the approximation guarantee, we can speed up density greedy a little bit, so we can get a nearly linear time implementation of density greedy using something called lazy approximate evaluations. So we can bring that slightly down to roughly n to the 4th. So that is idea number one. So idea number two comes from it takes inspiration from a different kind of algorithm for Knapsack. Namely, if you think about the FP test that packs items, so we guess the value and we find the minimum cost needed to achieve that value. So this is one approach we have for the linear case, and it turns out that we can use it in the setting as well. So what is the idea? So the idea is that instead of actually enumerating over these first few items that we consider to be valuable, so instead of actually enumerating over them, we're instead going to try to enumerate over their marginal values. So the marginal gains that they get on top of the items that come before them. So we'll have a small subset of valuable items. And for those, we can afford to guess their marginal gains. And of course, there will be the rest of the items, and there are way too many of them. And for those, we can no longer afford to guess their marginal gain, but what we can guess is their total marginal value on top of opt1. So if we guess this, then we can try to use an approach similar to the classical knapsack, where we are greedily picking items in order to achieve these marginal gains. So this is not quite an algorithm, and actually turning it into an algorithm is non-trivial. And this is where the previous work, a very nice paper by Ashwin Kumar and Jan Vondrag, comes in. So using this classical approach, together with the multilinear relaxation framework, they were able to get a faster running time for the submodular knapsack problem. So they want to leverage the multilinear relaxation framework, which is in some sense necessary in the setting in order to achieve this kind of approximation guarantee. But they also want to use these enumeration ideas that I just mentioned in order to make this as fast as possible. So their idea at the high level is that we'll have these large items, like the setup one that I had on the previous slide, and we'll have these smaller items like the setup two. And for the large items, we can afford to guess their marginal gains, and we'll use those to pack them using continuous greedy. Right? So now we're solving a continuous problem. And for the small items, we're only guessing the total marginal gain, and we'll use continuous density greedy to pack them to achieve that gain. Okay. So it turns out that we can implement this carefully and get a fractional solution, which we then could round without any loss and get an integral solution. And what this allows us to obtain is a nearly matching approximation guarantee in time that is essentially nearly quadratic in n, the number of items. So you can think of ignoring epsilon. So for so the whole name of the game in this talk would be actually improving the dependency on n. The dependency on epsilon it's quite high. So this is a somewhat impractical algorithm because of the dependency on epsilon, but it's theoretically interesting for reasons that perhaps will become a little bit more clear later on in the talk. So if you think of epsilon as a very small but fixed constant, this is nearly quadratic. Okay?
So Alina, just to make sense of this thing, am I is opt1 like 1 over epsilon to the 8th items, and I'm guessing that's...
Yes, exactly. That's exactly right. So opt1 is poly 1 over epsilon items, and we're enumerating over those values, and this is where this dependency comes from.
Wait, so the 1 over epsilon to the 8, that's an actual 1 over epsilon to the 8, not a big O 1 over epsilon to the 8? Or?
You're right. So I should probably have put the O in the exponent.
Okay. There's an O in there too. That's pretty
Yes. So let's just say that I'm completely ignoring those kind of dependencies. Yes, you're absolutely right.
So if the cardinality constraint was the fastest algorithm?
So there for cardinality constraint, we can do greedy, the standard discrete greedy, using sampling ideas to get it in linear time, nearly linear time, with a very good dependency. So n over epsilon times log of n over epsilon. So it's very nice and clean there. So when we go to the knapsack setting, things seem to get much more complicated if we're shooting for 1 minus 1 over e minus epsilon. That's a great question. So set up at a very high level. So again, shoving under the rug all of these dependencies on epsilons, the takeaway message is that we can solve the multilinear relaxation in time that is nearly quadratic in n. And after that, we can run the solution very easily in nearly linear time, so this is not a problem. So really, the bottleneck for the running time is the continuous step, where we solve the continuous problem. But if we step back for a moment, we might ask, okay, but where is this quadratic running time coming from? And it turns out, actually, that this algorithm is actually very efficient in some sense. Why? Well, the reason is that it's solving this continuous optimization problem, and it does so by evaluating the objective only a nearly linear number of times, which is a very nice property. It's essentially as efficient as we could hope for. So the only caveat is that every time we evaluate this multilinear extension, this can be quite costly. So in terms of the number of times we're evaluating the original function, and we most of the time we spend order n evaluations. So that's why the running time is overall quadratic. Okay. And for those of you who have thought about these problems before, you'll immediately recognize that this is just a very simple instantiation of a broader phenomenon. So this is essentially what happens in the setting where we're using the multilinear relaxation and rounding paradigm. So this is a wonderful framework because it's incredibly general, and it allows us to get nearly optimal approximation guarantees for a large family of constraints. But it comes with this technical challenge that when we relax the problem and we go to the continuous setting, what we want to do is to optimize the multilinear extension. And as we saw, Ashwin and Jan pushed this approach to the limit for the knapsack problem, in the sense that they achieved a nearly linear number of evaluations. And despite of that, the running time still ended up being quadratic. Okay, so there seems to be a fundamental bottleneck here when we employ this approach that makes it very difficult for us to achieve a number of evaluations to the actual function that is subquadratic. So if you want to think about this challenge from the conceptual point of view, so it's exactly the same challenge conceptually arises from the generic use of the multilinear extension. So even if we make the continuous optimization part as efficient as possible, if we're using the multilinear extension in a generic way, it's very difficult to avoid quadratic time. Okay. So how do we reason about this challenge? So this was our initial motivation for looking into the knapsack problem. So we wanted to focus on the knapsack problem because it's the simplest setting that we know of where this problem arises. So in the cardinality case, we don't face this challenge because we don't solve the continuous relaxation. But in the knapsack case, we do. Okay. So going back to the knapsack problem. So what are our specific contributions towards this goal of understanding whether we can do better? So what I'll show you today is an algorithm for the knapsack constraint whose number of evaluations with respect to the original function f is nearly linear as opposed to quadratic overall. And the reason we're able to obtain such a running time is because we do not use the multilinear extension in a generic way. So we're actually very careful about how we use it. So in particular, we make sure that the solution, the fractional solution that we're constructing, has a very bounded fractionality. in the sense that the number of entries that are strictly fractional, so they're not 0 or 1, this number of fractional entries is actually a constant that depends on epsilon. Okay, so this is the way we get around this difficulty. So this allows us to make sure that when we evaluate the multilinear extension on one of these fractional vectors, we do so only at a cost of a constant number of value queries, as opposed to a linear. Okay. And for those of you who are interested, the overall running time has a nice dependency on n, it's n log squared n, but it has this very high factor that depends on epsilon, much like the previous work, which we actually based our algorithm very heavily on the previous work. So there's much to be done in terms of improving this dependency, but we were only focusing on the dependency on n. So in the rest of the talk, I'll try to give you essentially the whole algorithm, modulo some details, and to illustrate how some of these ideas play, and how precisely do we ensure that the fractional solution has only very bounded fractionality.
Question. So
Yeah.
suppose I didn't want 1 minus 1 over e, but something worse approximation with a much faster algorithm.
You can do greedy. You can just get a half approximation very fast, yes. So that's true. So this is all in the name of getting very close to 1 minus 1 over 8.
Will you comment a little bit on rounding? So you said it can be done in linear time. So basically,
I'll show you how to do the rounding, yes. Any other questions? All right, so as I mentioned, so our algorithm conceptually is very similar to the previous one that Ashwin Kumar and Jan had. It's just a different execution. And the picture is really what we had before, which I'm going to make a little bit more precise. So if you remember this picture we had at the very beginning, so I was thinking about the optimal solution as being ordered according to this greedy ordering. And I'm thinking as the first few items as being up 1. So these are the valuable items. And for us specifically, the number of valuable items that we'd be interested in is about 1 over epsilon cubed. You'll see why that is. So the first 1 over epsilon cube are my set up 1. And then the rest will be up 2. And we want to do, so we want to solve the multilinear extension relaxation for the knapsack problem using some guessing for the marginal gains for the items in up 1. So I'm going to break down the algorithm based on these two sets. So my algorithm will have 2 components. One is trying to make sure that we're actually finding these elements that are in up 1 or getting a value that is comparable to theirs. And the other part here will be devoted to the elements in up 2. Good. And we'll do this over several iterations because in this case, it turns out, for reasons that I will not go into, we need to increase our solution, fractional solution, a little bit more slowly, right? So we're doing things greedily, so we don't want to increase too fast. So we'll do several iterations, and there'll be 1 over epsilon of those. Okay? So let's focus on a particular iteration. So the first part of the algorithm is trying to get items that are comparable in value to up 1. So specifically, what do we do? So for each of the items in up 1, so remember we have 1 over epsilon cube of them, we can afford to guess, approximately guess, the marginal gain of that item on top of our current fractional solution. So this is what this is. So this is the marginal gain of that item on top of the fractional solution. And we'll guess that value, approximately, appropriately discretized. Let's not worry about that. And once we have this guess, we're going to look at all of the elements whose marginal value on top of the current solution exceeds that. And among those, we'll pick the one of minimum cost. This is very much in the spirit of the FP task for Knapsack, where we want to reach a certain target value at a minimum cost. So we'll find this item, and we're going to increase its fractional value in the fractional solution by epsilon. So we're fractionally increasing it, but only epsilon at a time. Okay. So this is what we'll do in an attempt to make sure that we're covering up 1. Okay? So how about up 2? So for up 2, we can no longer afford to guess the individual marginal gain of each of the items in up 2 because there's just simply too many of them. So instead, we guess the total marginal gain that up 2 has on the top of the fractional solution. So this is the gain. So if we were to add all of up 2 on top of our fractional solution, this is how much we would be getting. And here I'm cheating a little bit. So what I wrote on the slide is not exactly correct, but it's morally what we want to do. And I'll come back to this. But for now, so what we want to do is to use just density greedy to pack items integrally to try to reach some fraction of that marginal gain. How much? An epsilon fraction. So we want to do everything in increments of epsilon. So we are actually going to use density greedy to integrally select items to reach a marginal gain of epsilon times this total gain that we guessed. And the key point here is that we're picking these items integrally. So here we were picking items fractionally, and here we're picking things integrally. And of course, by density greedy, I mean lazy density greedy so that it runs in nearly linear time and so on. So morally, this is the algorithm with some minor details that I'm shoving under the rug for now. Okay, so does it make sense? So we're fractionally packing items proportional to opt1 in this opt1 phase, and then we're packing items using density greedy integrally from then on. And we do this 1/epsilon times.
So where do you get those large value items from?
So this is all for the thinking. So we don't know which are the large value items. So for me, the large value items will be the first 1/epsilon cube items in the greedy ordering of opt. So this is just for the purpose of explaining the algorithm. So this algorithm doesn't know which of those are, but the guesses are designed to be the guesses for opt1, which are the first 1/epsilon cube items in the greedy ordering. And this guess is for the total gain of whatever is left. Why am I calling it the large value items? So it's because as I go further along in this ordering, the gain on top of what came before starts decreasing more and more.
So the complexity of finding that greedy ordering is...
Yes, exactly. So this is the greedy ordering of opt only.
So what's the complexity of that?
We're not computing this. This is just in our head, right? Just for the purpose of designing the algorithm. So the actual algorithm only guesses some values, which we think of as being guesses for the marginal gains of these items. We have no idea who they are. Make sense?
So you're just guessing the sequence of values.
That's
You're
right.
not guessing the items at all.
No, we're not guessing the items at all. So exactly. So this is the second kind of approach that I mentioned, where instead of enumerating over the actual items, we're enumerating over their marginal values, in the hope that we'll gain some speed up in the running time. Okay. Good. So this is the algorithm. So what is happening? So it's constructing a fractional solution. So what can you say about it? So the first thing we can do is analyze it and understand its fractional value. So what we can show is essentially what we were hoping for, that the value of the fractional solution is almost a 1 minus 1 over E approximation of the optimal value. So we can show this with some work. I'm not going to go into the details here. But we can say more about this fractional solution, which will be very helpful. So let's think about what is happening to the fractional solution. So in particular, let's think about what is happening in the up1 phase. That is the only part where actually we're we're increasing the values of items fractionally, because density greedy will pick everything integrally. So if you look at our fractional solution that we get at the very end, it will only have items that are strictly fractional if we selected them in this up one phase. And in the up one phase, we put the fractional mass only on 1/ε⁴ of these items, because we do 1/ε iterations, and in each iteration we consider 1/ε³ items, because that's our target. So up one has size 1/ε³. Okay. So this fractional solution has very bounded fractionality, and most 1/ε⁴. And moreover, from the way we design the algorithm, actually we can map these fractional values to up one. So we designed them to be proxies for up one. Okay? So the way you can think about it is that we have these 1/ε³ items in up one. And for each of them, in these iterations, we picked about a 1 unit of fractional mass, and we distributed it among some elements. So these elements here, they represent 1 unit of fractional mass, and intuitively, because of the marginal gains, we can charge it to O1, because we pick these items, of course, no more than O1, and so on. So each of these items has 1 unit of fractional mass that is supported in items whose cost is no more than their corresponding cost. Right, so this is what we gain by guessing the marginal gains and picking according to them. How does this help? It helps us in rounding, and this brings me to your question. So we can use this to round the fractional solution while preserving the fractional value. So we do not want to lose any of the fractional value. And at the same time, we want to bound the cost of these fractional items that get rounded up to 1. And because of this mapping that we have in our heads, we can actually make sure that the rounding does not exceed a budget of whose cost is no more than the cost of up to 1, which is exactly what should have happened in the ideal case, because these are all proxies for up 1. Okay? And I can very briefly show you how this works. So actually the intuition, for those of you who have seen this before, the intuition is very easy. So when you look at this, the first thought you might have is that, well, surely we can do this. It's almost like a partition matrix, right? So I have 1 unit of fractional mass, and I need to pick one of these guys representing O1, and so on. And indeed, this is almost the case, except that some of these items are actually straddling the boundaries. So they might be fractionally assigned to 2 items. So we need to make sure that when we round, we do not independently choose E3 here and also here. Okay? But that's the only catch. So if we do this a little bit more carefully, so specifically what we do is that we sort the items in decreasing costs. And we do, for example, just basically swap rounding with 2 elements at a time. And these elements are the ones that have the highest cost.
I'm not sure I understand the precise problem. So you have a fractional solution with the 1/ε³ fractionality.
Yes. And these are all, so these are only the items that are fractional, as in not 0, 1.
Yeah, and what other properties? Do you have a budget on the size? No.
Yes. So I want to make sure that they don't cost more than up 1. So this is what
Cost about.
No, but yes, that's a good point. So we did not guess anything. So I'll get to that in a minute. So for now, sort of intuitively, you should think that ideally, if I did everything right, then what I should add up in the purely fractional things should have value like up 1 and cost like up 1. And what I did in the density greedy phase should have value like up 2 and cost like up 2, ideally. Whether we're in the ideal case is not clear, but at least for the up 1 phase, I can convince you that I can reach the ideal state. I can round those fractional items and pay cost no more than up 1. And we'll deal with up to in a minute.
Wrap up.
Yeah. So we just do this a little bit more carefully, and basically we just do swap rounding according to cost, and I'm just going to go through this very quickly. And every time, so we move fractional mass, and just like we would do in swap rounding where pipe is rounding, and we can every time an item gets rounded up to 1, we can pair it up with someone in up 1, so they simply disappear, and that's it for the rounding, for that part. But as Chandra points out, there's also the up to phase that we need to worry about. So this one seems very harmless. We can round, be within the budget, but what we do there. And the main difficulty is really that we need to ensure that the density greedy phase does not exceed the remaining budget, which is 1 minus the cost of up 1. And this can be, so as I stated, this algorithm doesn't quite do that, but there's a very simple modification of this. And the reason is that really, in some sense, all of these items in up to can be, you can think of them as having small costs. So unfortunately, they do not have small marginal gain on top of the fractional solution, which is where the problem is. But we can just fix this using more guessing. Okay, so I'm not going to say any more than this. So basically, we're going to guess a little bit more than what I said, and it's very easy to fix. Okay, so just to wrap up, so in this talk, we focus on maximizing submodular functions subject to a single knapsack constraint. And our overall goal was to understand whether we can improve the quadratic dependency on the running time that seems to be inherent in the multilinear extension framework. Of course, there's much more work to be done. As we've already discussed, the dependency on epsilon is rather poor. It would be very nice to improve it. Maybe we can do even something in the spirit of the p-task that we have for linear functions, where the dependency on 1/epsilon is very good. And of course, the knapsack constraint is only a starting point. So we looked at it specifically because it seemed to be one of the simplest settings where understanding the quadratic barrier seemed to require a lot of work. We're very much interested in matrix constraints as well. So I think this is a very interesting question. How do we go beyond quadratic for matrix? And even partition matrix is open.
Thank you very much.
Thank you.
Since we're over time, we can ask offline questions for